I didn't even use appropriate significant figures. I should have done that based on what I've told you before. Let's just put that there. Okay, now we have good significant figures. But in any case, it's it's 4.4. So again, if you have pKa and it's pKa is 8, then you can readily convert that to a Ka just by doing the anti-log. So if if you have a pKa equal to some number, let's say 8, then the Ka is equal to the anti-log, or 10 to the minus pKa power. Okay, so Ka is equal to 10 to the minus 8. Okay. All right. So hopefully everyone knows how to do this. Acid-base chemistry will come up throughout your time here at Berkeley, so it's good to have a good foundation now. It'll save you a lot of effort later. So another great equation to then apply once you understand pH and pKa is the Henderson-Hasselbalch equation. And again, we'll go with our terephthalate dissociation reaction. So we have this nice reaction. And we'll, again, write out the acid dissociation equilibrium expression. So we can take this expression, and what we want to do is we want to basically, put in this equation, the pKa and pH, and then use that overall result to determine, say, what the balance of the two different forms of TPA will be. So to do that, you just take the log. The log of this entire expression. Okay, and you can use your log tricks. The log, now we have the log just of this ratio as its own isolated quantity. And we have now the log of the Ka and the log of the proton concentration. But remember that those are related to the pH and pK by minus, a minus sign. So we need to sub in here and here, and that's pretty straightforward because that's minus the pKa there, and this is, of course, the opposite of the pH. So we can say minus pKa equals minus pH plus log 10 of this ratio, TPA to minus over H, TPA minus. Okay, so now I'm going to rearrange this because we want to say, well, okay, if I had, it depends how you want to deal with the equation, but generally what's given is a pKa, and say, you mix together some ratio of two different forms of this acid, either a completely deprotonated form or the singly protonated form, and then you say, well, what's the pH going to be? Or, any given sort of situation where you have one unknown, and so maybe another way of thinking about it is let's write this out in a format where everything has a plus sign in front of it. However you like to think about it. You could use this equation in any state you'd like, and some people don't even like to bother to memorize the Henderson-Hasselbalch equations. They're like, well, I know what the Ka expression is. But this is a very sort of quick and dirty way to do it if you're given pKs and pHs, which is generally what you get. So that's the Henderson-Hasselbalch equation, as typically you'll see in textbooks and so forth. And like I said, it's pretty useful. We could say well, we know the pK of our particular ion is 4.4, and we could say we could ask the question at pH 5. Then remember before the example was at pH 4. What is the ratio? And we say ratio, we're meaning this again just to keep it simple. There are many versions of this calculation you can do, but I'm giving you pretty much the easiest one just because so we have enough time to get to the end of this lecture. And the ratio of these ions. But now instead of being at pH 4, we're at pH 5. Okay, so you just plug and chug, really. It's not too hard. So 5 equals 4.4 plus log 10 of this ratio. And I'm just going to call it ratio to be short and sweet about it. So that's going to be positive 0.6 as equal to the log ratio. And so we can, I think I'm out of real estate, so yeah. 10 to the 0.6 power, okay? And you might say, well, what's that number? Turns out it's darn close to 4. Okay, that's kind of cute, isn't it? If you like numbers, numerology, that's an interesting one. Okay, so that means that there's 4 times more TPA2 minus than HTPA minus, okay? And effectively, there's 4-fold more. So in this case, really, there's 4-fold higher TPA2 minus concentration than, that's a than, and than the protonated form, and that's because the pH is 5. So the proton concentration is lower than the Ka, or in this case now, the pH is greater than the pKa. When the pH is greater than the pKa, then you're not going to be able to fully protonate. That species is going to be largely deprotonated. So you have to be careful how you think about this in terms of greater thans and less thans. But when the pH is greater than the pKa, the reaction favors the deprotonated state. Now, I will say a few caveats here about our particular terephthalate reaction. Of course, the first pKa is about 4.4, but the second pKa for that second carboxylate is going to be about 6. So you'd actually have a slightly more complicated reaction if you were to think about the whole. It's sort of beyond the scope in this class, but some of you might ask. And why is it harder to protonate the second? Why is it harder to protonate the second site than the first site? Well, that's because the overall charge has changed, and various other things have happened to this conjugated pi system. And so you might imagine that the second pK is harder than the first. All right. So, how much time do we have left? Okay, good. We're in good shape. So the title of the slide is how to use acid-base indicators, but what I realize is before we do how to use the acid-base indicators, one might first want to know how to graph acid dissociation reactions, and then that will be very illustrative on how to deal with acid-base indicators, which we'll do next time. And then we'll do a clicker question. So we're going to do a graph. We're going to graph, and graphing is a very important skill. We're going to graph the TPA2 minus ion, and we're going to do that in blue. Okay, that's the key here. And then we're gonna also graph the protonated TPA 1 minus, and we're gonna do that in red. Let's say that's not what I did last time, but that's what we're doing today. And we're gonna do this as a function of. What do you think we want to do this as a function of? Any ideas? What might we want to graph these species using the Henderson-Hasselbalch equation as our guide as a function of the pH, right? Okay, let's make this crazy graph. X-axis, pH. Okay, that's our independent variable. Put some tick marks on there. Say 1, 2, pH 3, right through the relevant range, right? We did pH 4 and 5 already. Well, the other points will just sort of extrapolate our knowledge to 8. Then let's give this a double. This is a fun graph here, double Y. Okay, and we're going to say, the total amount of TPA 2 minus and HTPA minus is 1 millimolar. Okay, so you can't have any more than 1 millimolar of either species at either extreme of this particular plot. 1.0 millimolar of, this is the HTPA minus concentration in units of millimolar, and this is the concentration of TPA 2 minus, again, in the same units of millimolar. All right, so let's first think about the concentration of, let's see, our first data point. Our first data point was at pH 4, okay? And we're going to think about the TPA concentration at that condition. Remember that the ratio, so the ratio at that condition of TPA 2 minus over HTPA minus was 0.4. Okay, so you have to solve this little equation where 0.4 is equal to x over 1 minus x. In any case, when you solve that little equation, you'll get a value of about 0.3. And we need to put some tick marks on here. So 1, 2, 3, 4, 5. So halfway point is right here. So 0.3 is somewhere around here, approximately. And so that's 0.3 millimolar TPA 2 minus ion. Remember that at that condition, we have more protonated form than deprotonated form. And we can easily say, well, the protonated form is going to be up here around 0.7. Okay, so that point's up here. And this is for the HTPA 2 minus. And that's going to say be around 0.7 millimolar. Okay, so that's, we only have one data point for those two species. We have one other spot on the graph that we know well. And at that spot, we know that the TPA 2 minus to HTPA 1 minus ratio is 4 to 1. And you should be able to work that one out in your head without even using your little x over 1 minus x equals 4 equation as being 80%. Okay? So now you're 80%, and that's somewhere up here, or 0.8 millimolar TPA 2 minus. Okay? And that means the balance is going to be 0.2 molar here in red. Okay. Does anybody know what the magic point is on this graph where exactly TPA is equal to HTPA? What's that pH going to be? The pH is going to be the pKa, and just so we can use all the colors that we have. That is the magic point here where the pH is equal to the pKa, which is 4.4. Okay, so there's lots of 4s. It might be driving you batty, but that is what we have. And that is right at the balance point here of this titration. And so we have a red point and a blue point right on top of each other, and 0.5 millimolar TPA 2 minus there. And so these are the data, HTPA 1 minus. Okay, so now we have kind of a curve, and I'm going to, the spoiler is going to be just rolling it in here. I mean, we're not going to calculate all these points. We don't have time. We want to do lots of fun things like clickers. But we're going to have this nice smooth curve that looks like this. It's a sigmoid, okay? It's S-shaped, sigmoid, like this, sigmoid. S-I-G-M-O-I-D, and we're going to have basically the opposite shaped sigmoid here for our 2 minus ion. And remember that can only go to 1. And so that means at very low pH, you favor the protonated species. In fact, well, you would have favored the doubly protonated species. I know I've sort of taken some liberties in this demonstration. It's not chemically correct, but in any case, you favor this protonated species over this deprotonated species. And that is effectively what a pH titration curve would look like for these, if you could actually monitor these individual ions as you went. Now, that's not how you'll experimentally determine this. We'll do that next time, but you'll get into that. That'll be the following lab. But at least you've got a good intro into how to do acid-base equilibria. So, okay, are people caught up with this page? I know there's a lot of information on that. But get out your clickers if you're already caught up, and then I'll get the question fired up. Okay, so this is the question. We have plenty of time to do this because I didn't dilly-dally like I did last lecture. That we're going to consider this general acid dissociation equilibrium. So the general acid is A, and the protonated form is HA, and that goes to H plus, a proton, and the dissociated form of the acid A minus. And that has a Ka of 10 to the minus 6, so tell me what the pKa is, and hopefully everyone can do this. It's pretty straightforward. We don't need a calculator, I hope. And then I'll go over the answer in a minute. You're welcome to use a calculator if you need to. Okay, has everyone clicked in? 413 of you? All right. So, oh, I should first check to see how you guys did here. I showed you the answer first. Somebody was holding back. I saw that. No. Wow. Okay, so most of you got the right answer, which was C, and a few of you picked A and B, and I don't know about those guys that picked E. Anyway, the equation for computing the pKa is straightforward. Just take the log and then take the opposite of the log. And so the log would be -6 and times -1 plus 6. So, all right. See you next time.